I think, the most important one is being sort of polymathic. It's like an extension of being curious, but basically being interested in everything
Mhm.
means that you're able to spot connections across disciplines. And often some of the most transformative moments have been interdisciplinary.
This is the Once a Scientist podcast. I'm Nick Edwards. We're back with new episodes, so keep an eye out and subscribe to the podcast if you haven't already. Chris Anderson is an advisor at Pillar VC and a senior advisor at Renaissance Philanthropy. He's got a really cool background, and I think many people that are listening are probably familiar with your work because you've been kind of in this space for a little while. Chris, you've got a really interesting career. I'd love for you to piece it together a little bit because I know you started out as a scientist and working as a physicist, then spent some time as an editor, both at Nature and Science. I think you're the senior editor at Wired.
I was the editor-in-chief.
Okay. All right. And editor-in-chief, and then wrote a couple books, one of which was a New York Times bestseller. You spent some time in the maker community, were a CEO of a robotics startup, and now you've been interested in DIY labs. So super excited to have you on. And thanks for coming on the podcast, first of all.
Thanks. It's hard to make my career make sense, although every step of the way, it did. But basically, scientists sort of, not a good enough physicist to be a physicist, and so transitioned into media, science media in particular, and then tech media, and then got back into tech through drones. So that's the robotics we did. We're flying robotics, and sort of it helped start the modern drone industry that was kind of cheap and low cost. And my single stupid trick is I put the letters DIY in front of industries to see what happens. So DIY drones became a community, including technology that we built in open source.
You started out as a physicist. How did you end up moving from that into editing? And tell me a little bit more about kind of some of these transitions, because it's always good for, I think, junior people to hear the different ways that people move through science in these different careers.
So physics in the middle of the 20th century was incredibly exciting. As a teenager, I dropped out of high school and was a truant, but for the best possible reason, which is I was reading the Feynman lectures in the library
Oh, yeah.
rather than going to classes. So, the 20th century, between the Manhattan Project and Feynman and quantum mechanics, physics was the kind of the golden scientific domain. And so, I aspired to do that. But by the time I was 27 years old and going back to college and doing physics, two things had changed. It was now, the world's best physicists were coming to. I was at Berkeley, and the world's best physicists, especially in China, were just now showing up, and they were just unbelievably good. Second is that physics kind of fizzled out for a kind of interesting reason, which is that any scientific domain, as the sort of gap between theory and experiment can only be so big. In physics, if you have a theory about some particle, and you can test it within 3 to 5 years, that's great. And, it's either falsifies or doesn't. If the experiment falsifies the theory, then you come up with a new theory. If it confirms the theory, then that becomes canon. That sort of finite gap between theory and experiment is super important. The problem with physics, at least the kind of physics I was doing, which is particle physics, is that you're basically trying to get closer and closer to the Big Bang, which has more and more exotic particles that only exist at higher and higher energies. And the problem is that the cost of those particle accelerators, because we're talking about 10-mile diameter underground rings. And then, 20-mile and then 30-mile, they're just massive.
How many of those can you make in the world, right?
How many can you make in the world? So basically physics got harder, and I was not, among the best. And so the funnel shrank. And so my whole generation of physicists came to the same conclusion I did. And almost everybody at that time went to Wall Street to become a quant. They dealt with high performance computing. They were good at math. They were good at programming. And the next adjacent space that had those things was Wall Street. They got paid a lot better there. So almost everybody went to Wall Street to become a quant. But the other thing that happened in the physics labs at that time was the internet. That the internet was designed to connect physics laboratories to share things like supercomputers. And the web was created at CERN in Switzerland, that physics facility. So physicists were like, crap, I can't do physics. What can I do? And the answer is you can do Wall Street or you can do the internet. And I chose path B, and that took me into, then I went into the journals, Nature and Science, and then the Economist, where I was for 7 years. I increasingly started realizing I was doing less science and more sort of internet coverage, and that took me into tech.
Interesting. Do you feel like you're kind of coming back home a little bit? In the last little while, you've been looking at DIY labs, or
Exactly. I mean, so after I did sort of robotics and AI and both drones, and then I did full scale aircraft,
Uh-huh.
was developing air taxis, and then went from there to a kind of a spin-off that was working on AI advanced manufacturing, basically still sort of thinking about how would we, if we, we're going to redo the industrial revolution in 2026 or now, how would we do it differently? Both
Yeah.
from the design side and the manufacturing side. So that gave me a real sort of familiarity with, like, it's a good time to like rethink any industry from first principles. And I thought, what is like adjacent to that? I realized that, science is kind of a form of manufacturing. You're generating, I mean, you're working with atoms. Those atoms could be molecules or cells and things like that, but you're basically working with the physical world. Although much of manufacturing is now already automated, as I discovered, not enough of science is automated. That was fine for decades. You just throw grad students, at it.
Yeah.
But when AI kind of enters the picture, and this plays entirely to your strengths.
This episode is brought to you by Potato. We're building AI agents for closed-loop autonomous science. Check it out at potato.ai or email us at hello@potato.ai if you want to figure out ways to collaborate.
When AI enters the picture and AI is generating candidates, you have a hypothesis, AI suggests some paths to pursue. AI can generate candidates faster than you can do them.
Yeah,
and so
absolutely.
You basically need automation to
and better
keep
ones.
up.
And better ones. Yeah.
And better ones. But the reality is that any AI needs to be validated. It needs
Right.
to be ground truthed because it'll start hallucinating. And so, like I was saying before, if the gap between theory and experiment gets too big, then theory becomes not just hallucination, but almost like metaphysics. It's like philosophy. It's like poetry. It just sounds good. And so you got to keep that kind of theory validation loop pretty tight. And because the AIs are generating hypotheses so quickly or candidates so quickly, that the only way to validate some significant fraction of them, so to keep them honest, is to automate the process. And
Yep.
so here we are.
That's something I think about a lot, is just like, how do we close that gap? How do we close the loop faster? I mean, we'll never get to a commensurate degree of the amount of hypotheses you could test, but at least we can widen the funnel, right?
Absolutely. And you don't need to test everything, but you need to test some representative samples so that you can, establish that the gradient is accurate. I had a really interesting conversation with Andrew White from Future House now.
Yeah,
Edison.
he's great.
I was saying, because I'd worked in the publishing industry and I needed the publishers like Elsevier. I was like, if we could write them a check so that they would open up all their paywalled papers so that the AIs could learn from it, what's that worth? Well, he thought a little bit and he sort of said, it's probably worth, it's a decreasing amount over time because, we're generating more data faster than the old did. And then he pondered for a bit and then he came back and said, nothing. I don't think it's worth anything. I was like, wow. And he says, we can now generate new data so much faster and higher quality data. And data has all the metadata that you described. Not just like, a one paragraph obfuscated method section, but like literally the code that ran the machines that generated the data. And this replication crisis we have, I mean, how much of that is due to slop or error or fraud? And how much of it is just due to the fact that people are not precise enough in what their methods are. And so it's impossible to replicate them.
Yeah, 100% agree with that. I think, obviously you want to stand on the shoulders of giants, and that's part of what we do when we go and read and really deeply understand an area and a body of literature. But it's really just like vectors for thought and, the ability to give you to help you develop that taste, right? And so that you can then use the tools to allow for the throughput and to test, any number of hypotheses within, kind of like that given vector.
The Genome Project was what, $3 billion for the first genome? I can't remember. Was it? Do you remember how much it was?
I don't remember. It was in the billions though, for sure.
Well, let's say it's 3 billion, and now it's like 3,000, right? So if you could sort of rerun the 20th century's, key science at 0.1% of the cost of doing it the first time, and this time it's going to be super reliable, I mean, you wouldn't redo everything. It's certainly asking a question, so in physics, for example, what you do is you have what's called a cross-section of particles, which is basically how big are they when they, how big do they appear in collisions? And the first time you do it, your error bars are like this, and the second time you do it, your error bars sort of shrink over time.
Yeah.
And there's a lot of value in just getting more decimals of precision for any measurement. And so, getting, decimal like 27, adding decimal 27 to the previous 26 is not Nobel Prize winning work. It's important for a sector to kind of refine its measurement accuracy. And I think the same thing could apply to biology. This is an open question. I have nothing. I'm not a biologist, but let's say, take the PDB, for example, which I guess is mostly done with crystallography.
Yep.
Is that right?
Yeah, and it's like
Um,
pretty established methods that people are kind of running similar methods over and over. The same method basically
yeah.
to generate these
What
crystals.
if you redid all of them? How different do you think doing it with modern methods would be from previous? I mean, in other words, I guess how much error do you think there in the PDB?
I don't know. I'm not a crystallographer, like, so it's hard for me to have a real accurate description. But like, I think that the crystallography and the reason why we have the PDB is because people contributed obviously to this open source movement, and also there was an established standard for how to generate that data. And so I think with new methods, you could probably get to a better precision. You've already overcome a bunch of the standard deviations, right? Because
Mm-hmm.
people standardize these methods. And like that's something that we've been thinking about at Potato a lot, is because we built this tool for optimization of experiments. And it touches on the point that you're talking about, is you need to have really good assays that you know are working and have been optimized and can give you a strong signal to noise ratio, because like the challenge is a lot of data just is super noisy
Yeah.
because we don't have good standard working assays for them. So I really think that's the bottleneck, is getting really good standardized assays that allow you to generate the kinds of data that you could build, an AlphaFold with, or whatever the next modality that you really want to go after is.
I think the answer is now possible to gather data that's higher quality,
Yeah,
more precise, more repeatable,
absolutely.
and way cheaper than it was in the past. Obviously, going forward, we'll do that, and we'll share it, and we'll have like the proper repos, and we'll have the methods will be much more detailed. But I'm just wondering whether there's a case for going back and
Yeah.
repeating experiments on the grounds that not that they're wrong, but there's probably the error bars could be shrunk if you did it with modern methods.
I don't know for sure, but I think probably. I mean, it seems rational to me, because like that's the thing about science, is like it's continual progression. We move forward with new tools and collaboration. The fact that we have tools to be able to better design experiments, and those, I would imagine those crystallography methods have improved. So, yeah, I think it's an interesting question.
I
You
learned, by the way, how to crystallize proteins. Have you done crystallography before?
Nope.
Have you crystallized?
Nope.
It's so cool. I mean, first of all, it's crazy hard,
Okay.
and and there's
I
like
hear it's
there's a
an art
rough.
form. Yeah, it's an art.
I may get this a little bit wrong, so there's the scientists and the listeners will correct me. But what they were
Sorry.
explaining to me is that basically that you've got these like flash freezers, and that there's I think it was a Nobel Prize for like if you combine sort of it's not ethanol, maybe it's methanol or something like that. At the right temperature, the right pressure, it sort of instantly freezes. And so the water molecules don't destroy the protein. Um, but there's lots of knobs and dials in sort of like the recipe that does that. And
Yeah.
every protein has a different recipe. And, God willing, one of them works. And it's like, boom, that's the recipe.
Yeah.
But imagine doing that by hand, which they
Yeah.
did for decades.
I think that's pretty representative of basically all of science. My expertise was in electrophysiology and neurons, and looking at circuitry, and very much an art form, like dependent on individual hands and very specific methods.
Yeah. I mean, this is the classic thing in biology is like it worked on Tuesday, but it didn't work on Thursday.
Yeah, well, and
Why?
I guess that's one of the big questions I have about, like, when we think about robotics in the lab, and if you make the comparison to manufacturing, which is a world that you've lived. I mean, by the way, for listeners, Chris wrote a book called Makers, which has great reviews. Check it out. But talking about the kind of the future of manufacturing back in what, 2012, maybe? Is
Yeah,
that
this
right?
was, I think it was probably about then. It was kind of like inspired a little bit my experience in sort of becoming a drone manufacturer. I had no business. I mean, as a magazine editor, and I was messing around with Lego with my kids on the dining room table. And it's like, whoa, that looks like it could be a robot. And then it could be a flying robot. And oh my goodness, what's a flying robot? It's a drone. Anyway, going from that to being America's biggest, drone manufacturer was a crash course in manufacturing. And what I realized about it is that anybody can do it. We were just buying used machines on eBay and figuring out how to use them. And it's just like the Chinese turned out to be better at it than we were, but
Sure.
still, there was definitely a democratization moment, and 3D printing was part of that, and open source software.
That's one of the questions I have, is like, is science as modular as manufacturing? So I'm curious what your perspective is, because last time we talked, I think you said you visited around like 100 labs. What have you learned across that process about,
Yeah,
right now?
there's superficial similarities. You're definitely taking bits and turning them into atoms. There's definitely room for automation in both sectors. So let's take the three sort of major domains of science that at least that we're talking about, which is there's chemistry, there's material science, and then there's biology. Biology has the advantage of being basically room temperature, basically water-based. So you can do it pretty safely with regular folks, but we really don't have a fundamental model of what's going on there. It's incredibly complex. It's probably chaotic and emergent, and we're kind of groping in the dark. So the good news is that we can do experiments quite easily with automation. The bad news is that we kind of have to do experiments because we don't have a theory that will really guide us. I was just reading a book called How Life Works by Phil Ball, a former editor. I worked with at Nature, and one of his points is that the central dogma has been basically just doesn't apply anymore. We thought it was like, we got a theory. It's the central dogma. DNA creates RNA, which creates protein. Done. It's like, the fallacy of the Genome Project. It was like DNA is destiny. We're done. Central dogma. That's just not true. It's just way more complex at every layer and all emergent. So the good news about biology is that you can test it, pretty safely in a normal environment. The bad news is that you basically have to, because you can't just write a whiteboard the theory and expect it to work. Chemistry, periodic tables, pretty well understood. Chemistry is better, and we can't just sort of apply Schrodinger's wave equation at scale, and of course that's computationally irreducible and impossible to do. But at least theoretically, we could sort of predict things. Computationally, it's too hard. We can't do it. At least the theory is pretty solid. Material science. Kind of likewise, it's basically atoms interacting, the sort of wave functions, etc. We start with the solid theory, but we just don't have an ability to extend it to the macro phase of actual material science. The problem, of course, is with chemistry, you're dealing with high temperatures and caustic materials. With material science, we're dealing with powders or dealing with kilns. If you look at sort of the chaos of room temperature, the search for room temperature superconductivity, which typically is ceramic, what will happen is, you remember this, what happened is someone says, hey, I mixed these weird powders under these weird conditions and stuck it in the oven, and it came out, and I hit it with a hammer, and this one little fleck over there kind of levitated. Boom. And it's like, replicate that. And which they can't, because it's just so freaking like unique and one-off and not properly documented, and it's just freaking chaos. And so, all of science can benefit from better structured, more automated, better instrumented experiments, but all in different ways.
That's interesting. It reminds me, actually, my grandpa was, he had a friend that I think the 80s, he had made a discovery that went big, and everybody kind of knew about it, and it was cold fusion.
Wait, who was your uncle?
This is my grandpa's friend that we went to. I would go to lunch with him when he was older one time. But it ended up not being replicable, and he had a lab in his basement, still in his old age, in his 80s, where he was trying to reproduce this experiment at home after he had retired as a professor. And I was just like, that's the challenge. Is like, I don't know what the story is behind it, but I remember hearing the story when I was young. This is before I even went into science, before it was even a twinkling in my eye. That story's always stuck with me, and because I've had things that I remember seeing in the lab, and like, it was reproducible, and it worked for me over and over and over for a while, and then just went away, and like, I never published it because like I couldn't find it again. It's an interesting like tidbit of science that like is somewhat representative of the challenge of doing research, right? You've seen a lot of things. Like, you were a big part of like the internet moment when you have been part of this manufacturing push. Like, how are you spotting all these important waves? How are you seeing through the trees?
Yeah, a lot of it's luck, just right place, right time.
Okay.
That sort of thing. I didn't spot the internet as being a big deal. I just happened to be in the physics world at the time when the internet was being used to connect physics labs. In that particular case, I didn't even realize what I was sitting on until this magazine called Wired shows up in 1993, and there's just like all day glow and super sci-fi, and it was just like, the internet's going to. Actually, initially, it was even pre-internet, and they were like, the information superhighway is going to change everything, and it's going to be the end of the nation state. It was going to be a cultural revolution. I was just like, that nerdy thing I use every day in the lab is going to like change the world. So I would at least, in that case, I credit, Wired for illuminating the potential. But, once I saw it and I realized that they were right, I was like, well, I got to do it. And so I think that, in being in the right place at the right time is one important thing. Being kind of optimistic and sort of curious and open to new ideas, and sort of, and being willing to sort of like, get sort of excessively enthusiastic about them is also key. And then I think, the most important one is being sort of polymathic. Sort of, it's like an extension of being curious, but basically sort of having, sort of being interested in everything
Mhm.
means that you're able to spot connections across disciplines. And often some of the most transformative moments have been interdisciplinary moments. Like what I'm doing right now with like the AI scientist moment, you've got scientists, you've got AI people, and then you've got the lab automation people who are validating it. It's very hard, very rare to find a lab which is strong in all three.
Yeah.
And so it's a great moment for people who may feel that they're not, I'm not enough of a scientist to be useful in a lab, or I'm not enough of an engineer to be useful. It's one of these moments where it's just like, it's okay to bring your own skill set to the mix because we need all of them. It's quite liberating in many ways. And it's a good time to have, like, you have permission to enter areas that normally would have required a PhD in something. You have permission to enter because you're adding value in your own way. And this is why I call myself a value-added tourist, because I visit labs and they're kind enough to show me how they do their science. But what I can bring to bear is like, well, the engineering mindset. And I was like, oh, here's how you could do the automation, or here's how you could do the cameras better, or here's how you could sort of handle your data, better. Not because I know a lot about that particular science, but because you take a tool from an adjacent industry and you import it. And like one of the things I did recently is I was helping out with a lab that's DNA barcoding insects,
Okay.
where we have a huge backlog of bags of bugs in California in particular. It's millions and millions of bugs that were sort of collected, stuck in ethanol and bagged and stuck in a refrigerator. They don't really know what they got, and there's no real census of biodiversity of California. So the best way to do it is DNA barcoding, but it's these are bags of bugs, and there's like hundreds in each bag, and so you have to take them out. You have to put them under a microscope with a little tweezer. These are parasitic wasps that are like the size of like a period, the tiny things under a microscope. You take them out with tweezers. You take them out. You stick them in a well. You then put in the enzymes to digest their soft tissues, and then also. And they tried to automate him with like robot tweezers. I walked in and I was like, oh, my industry, electronics, you know how we pick up like tiny little things and move them? We had this thing called a pick and place machine. And it's electronics. You have spools of tiny little electronic components. You pick them up with a little vacuum with a little nozzle, picks them up, looks at it with the camera, and sticks it very precisely on a printed circuit board.
Yeah.
And I was like, I think we could just pick up bugs instead of like electronics. And by the way, I think that a standard open source pick and place machines cost less than $2,000. They are open source, so you can modify them. And I was like, I've got one. Just so happened I had one that I could borrow. Brought it in, literally codex, Claude Code, whatever, like 2 hours of like write a script that will not do electronics, but instead pick up bugs, look at them under a camera, and stick them in a well. 2 hours of codex, and the machine basically works. And we could potentially take an order of magnitude out of the cost of DNA barcoding insects by simply utilizing a off-the-shelf industrial machine from an adjacent industry that no biologist would have thought of, but any electronics guy automatically knows. Yeah. It was just the ability to sort of like import best practice from an adjacent industry and sort of say, look, you don't want a robot tweezer. What you want is a little vacuum with a nozzle. And those things you can buy them. It's like, who knew?
I love that. This is Kia Lab.
Kia, yeah,
Okay.
out of Berkeley. And it was a classic case where I said, can I visit your lab? I visited their lab. They showed me refrigerators full of bugs, and they showed me the problem tweezing them into wells. And I was like, looks like a pick and place machine to me. And it works.
Very cool. So if you're thinking about then like all these kind of experiences that you've had in these different, well, first of all, why DIY labs? Like what is it about AI science, this moment in AI scientists, like science that's driving you toward this?
Well, I mean, the DIY is it's just code for democratizing. Okay. Just make it, lower the barrier to entry so more people can participate. And we've had DIY bio for a long time. And it's struggled for reasons because biology is hard. I think that, in general, right now, because it is so interdisciplinary and because people who have skill sets in AI, but not necessarily, biology, or skill sets in automation, but not necessarily AI, it's the right time to just make it easier to participate.
Yeah.
Build community, open source the tools, make them cheap. Your company's entirely about making them easier to use. And anytime you can lower the barrier, you expand the participation. And when you expand the participation, you not only just get more labor, but also new ideas. And this is like the history of like at least the last 20 or 30 years, certainly the history of the internet is about democratizing. Just make it easy to make video, make it easy to do media, make it easy to, share code. Just make it easier. And I think it's science's moment.
Yeah, I love it. Tell me what you're seeing in terms of like where the future is going with lab automation. What does the lab of the future look like to you? How are you thinking about it?
Yeah. Once I sort of realized that lab automation involved automation, which is something I'm good at, but I needed to kind of baseline myself on kind of what the gold standard is in the moment. I basically visited a lot of labs, and I went to SLAS, the big conference. I think I met at SLAS, and I wanted to just kind of like say, where is the industry today? And the industry today struck me as being mature. It sort of had a kind of a 20th century conceit, which is largely about sort of the lab bench and the human scale stuff, by and large. And it was very mature. The enclosures were nice. The touch panels, were nice. They were sold, the pricing was like in, 50 to 100K. And machines were made in units of like hundreds. Maybe the number one liquid handler sells a couple thousand per year. In other words, it looks like a mature industry. However, none of it looked like it had been truly transformed by AI in a couple ways. I mean, first of all, a lot of them had proprietary interfaces, so they weren't easy to automate. And this is obviously the core of your business. They were also human scale, which is to say they were kind of boxes that would sit on a bench, and they were designed, they had doors that need to be opened by humans and sort of buttons that need to be pushed by humans. And the notion is that these machines, automated machines, work in proximity with humans. And so it's kind of a hybrid lab where you have humans doing some jobs and machines doing others. Imagine if a data center worked that way, where you basically sort of said, well, we have all these laptops and they're on benches. And, and then when technicians come in and sort of start programs on laptops. So imagine if a data center worked that way, as opposed to the way a data center really works, which is like it's lights out, everything's racked super high, the board, everything, all the computers are stripped down to their bare motherboard essentials. It's just optimized for scale. Yeah. And a data center will have hundreds of thousands or millions of, CPUs in there. What would a self-driving lab or an automated lab look like if you really put on data center, a hyperscaler kind of conceit? And, it's clear that you have a human scale science and then you have machine scale science. And machine scale science wouldn't have enclosures, wouldn't have touch screens, and they'd be designed to be racked really high. I think we're seeing glimpses of it, like the Ginkgo racks, for example, still sort of human scale, but at least there's no humans involved. There's robots and move things around from machines to machines and open doors when necessary and stick things on little trolleys that go on to the next one, et cetera. But even that's too expensive. What if like every experiment had a bespoke, not all experiments suit, microfluidics, but let's imagine they did. And that, you said, I want to do this experiment. The experiment's going to involve certain inputs and certain outputs. There's certain reagents that go in, there's certain transformations that happen, and we're just going to create a bespoke chip. Or it could be 3D printed, it could be, PCB fab or something like that. But a single purpose experiment that does like one thing properly. If it's a cartridge and it fits into a standard slot, and the standard tubes come in and come out, and it's like this big, not that big. I realize that doesn't suit everything, and obviously microfluidics and millifluidics are a thing right now. But you can sort of see that to keep up with the AI opportunity, we're going to have to sort of rethink the kind of human-centric approach we right now have to lab automation and go for things that are truly designed to be done lights out, no human involvement. And that's going to involve shrinking things to the bare minimum. It's also going to involve bringing in sort of gold standard automation from elsewhere, robot arms, humanoids, dogs, you name it. I mean, there's obviously the robotics industry is on fire right now, and there's a ton of innovation happening there. Companies like Medra are focusing on robot arms on the grounds that they have the ability to automate potentially every step of the life cycle, starting from the lab bench in basic biology all the way to like animals and plants, and then maybe even to the clinic and beyond, because A, they're incredibly flexible and they have lots of degrees of freedom and they can pick up things and all this stuff, and B, that you're surfing on the wave of all the investment that's going into general purpose robotics right now. Right now, I'm slightly on team robot arm, only because I think, to the pattern matching point you made earlier, you want to surf waves. And it feels to me that's the biggest wave right now. And although the robot arms are not as good right now in terms of this throughput as a single purpose liquid handler, they are getting better, faster. And you have the ability to sort of solve the inter-device problem, moving things from one place to the other without having to invest in expensive trolleys and, maglev tracks and things like that.
In some of the labs that you've been visiting, I mean, do you see people starting to implement robotic arms? I mean, I guess like Medra is a great example. They've got, I think, 100 workstations or work cells that they've stood up in a really short amount of time. So it's pretty cool to see. I think Ginkgo is a really interesting example from a commercial perspective. But are you seeing people starting to build these things in like a DIY setting, like smaller labs?
Just a bit. I mean, the learning curve is still higher than it should be. I mean, I think at the DIY setting, and I think you and I were talking about this really inspiring thread on X the other day, this guy who who kind of refined an Alzheimer's drug using an open trans in his garage. So I think for the DIY stuff, just like there's a lot of complexity. Let's make it simple. Just like use a liquid handler. Or it could be like either an off-the-shelf one, like an open trans, or you could repurpose a 3D printer. Then you need to close the loop with computer vision. And like one of the things I'm working on with the lab right now is just like in my world of robotics and manufacturing, everything has fiducials. Fiducials are just like April tags or little sort of machine readable, like a QR code. The nice thing about a fiducial is very easy for computers to read, and it tells you the orientation of the plate. Everything should have fiducials. Everything in the lab should have fiducials. And once you have fiducials, then the robots are like, oh, I can see, okay, now I can see where the plate is. I can see what orientation is. I can see its offset. I know how to pick it up. You can have stickers. You can like literally, I don't know why labs don't have like sheets and sheets of stickers with these little QR tags or QR codes or April tags. And just fiducial everything, put fiducials everywhere.
Yeah.
And what you've done is it's training wheels for the robots. Now they look around and it's just like, whoa, what is that? I've never seen this sort of, oh, that's an April tag. And not only do I know the tag, do I recognize it as a tag, I recognize its orientation. And because the tag has a unique ID, I know what it represents. It's like, oh, that's a test tube. Oh, and this kind of test tube is most easily sort of unscrewed with this technique that I've already learned. So basically, there's going to be an initial element where we kind of have to, if you want robots to come in, we have to kind of prep the lab to make it easier for the robots to kind of find the way around. But over time, they're going to learn, and there's things called visual language action models. And over time, just like if you drive a Tesla, all of the weird edge cases that you see all become training data for Tesla, the company. And the next model will incorporate that, and they just get smarter over time. You want a robot to be able to do one thing well, and that gives it like license to get into the lab. You have permission to come into the lab because you do this one job well. But once it's in the lab, then like, okay, foot in the door. Now you start to say, well, let's just like, what else could you do? And when you start putting fiducials around and sort of prepping the lab for robotics, then suddenly it gets a lot easier to do it.
Yeah, I think Hi-Res is doing some really interesting things around that, where they're tagging all the instruments in the the broader work cells, and basically it generates kind of a digital twin of the lab, and then their agents can reason across that for experimental planning. Very exciting, really cool stuff.
And it's just so easy. It's like literally sheets of stickers.
That's the exciting part. That's the challenge also, right? Is like we're serving an industry where the workflows are so variable. It's like, R&D by definition is like you're changing things constantly. And so how do you allow for that flexibility? And I think it's exciting times. So you're team humanoid, it sounds like. Team robot arm.
Well, I'm probably team robot arm.
Okay.
I played with all of them. The humanoids seem like overkill for the lab. I mean,
Agreed.
the humanoid has got
100%
legs and arms. If all you need to do is move the arms from place A, place A to place B, and stick them on wheels. Also, I mean, in some situations, the robot dogs are a better choice than the humanoids because they're stable platforms. They've got 4 points of contact. If you ask me like what my sort of MVP of automation is, it's a robot arm, a 7 degrees of freedom robot arm on a rail. So that adds, let's say it's 6 degrees plus the rail, or maybe it's 7 degrees plus the rail, so it's 8. That is the sweet spot right now. It's super easy to program. It has the ability, as long as the rail is, so it could be 10, 12 feet, moving up and down. It has the reach on both sides of the rail. The robot arms, the ones I like a lot right now are the Seed Studio Rebot, which is about $1,500. It can lift 5 kilograms.
Wow.
Incredible repeatability. Comes like ready to go out of the box. Actually, out of the box one's $2,000, but close enough. I program with the Hugging Face, stack, which is all imitation learning, which is really easy to use. Just really solidly made. And just to think that, for like $1,500, you can basically get a pro quality arm that is designed for AI. That was not the case 10 years ago.
That's crazy. It's totally crazy. In this future, like, how does the future look bright? How does it look bright for the individual scientists if we're automating a lot of work? Like, what is the role of researchers? What do you think?
Yeah, I mean, that's a really good question. Let's divide science. And again, this is kind of, maybe I should ask you this question. So I'm going to give you kind of a half-baked answer, but I really want to hear your fully baked answer.
Sure.
Let's divide science into sort of 2 categories. There's kind of novel discovery, and then there's sort of like optimization. So novel discovery would be like, I've got some crazy hypothesis and let's see if it works right. And, in that case, I think automation is probably a nice to have, but because it's by definition novel, These are protocols that had not been done before, maybe involving certain recipes or ingredients and things that have not been put together again. That probably, for the novel side, that's probably pretty good on, I think AI is going to be quite useful for lit search. So like Edison and the spin out of Future House is really good at sort of, crisping up your hypothesis. It's like, okay, I've done the lit search. Here's what I think about it. So just kind of like sanity checking your hypothesis or maybe helping you generate better hypotheses. But that's kind of purely on the AI side. It doesn't involve a lot of automation. Once you get then to the sort of like the process improvement, so it's like here I've got some enzyme that has a certain yield, or actually how do we measure the success, the utility
Activity.
of an enzyme?
Yeah.
Activity.
Yeah.
An enzyme has a certain activity, and if we can improve the activity, that has a huge industrial potential. That's an example, and you see this a lot in chemistry and material sciences and a lot of industrial processes where you have case of Pareto frontier, which basically we found a recipe that works, and you turn the knobs and dials, and this thing is like 40% yield. There's probably some recipe that works better, but this is like good enough. And who has the time to explore all the various other permutations of knobs and dials? Well, AI and automation has time.
Yeah.
And so we saw this, the Ginkgo experiment with OpenAI was I think it was a protein synthesis, experiment. And they basically just sort of like, you know what? We're just going to sweep across the domain range. That's like 10,000 different variations of knobs and dials of settings, parameters, hyperparameters, whatever. Let's just run through them all. Or if not all of them, let's at least sort of like, here's the Pareto frontier, and let's do a couple samples here and there. Ooh, yeah, this one seems to like a little promising there. Maybe there's a gradient. Let's explore in that direction. And that sort of classic exploration exploitation that AI is so good at is the way that we're going to sort of get better recipes with higher efficiency processes without a huge amount of labor. And that's for classic, it's groping in the dark. That doesn't sound quite right, but let AI sort of wander through the forest in the dark on our behalf, such that you can sort of find a better recipe. And that's that idea. So that you may not call that science. That's maybe closer to engineering, but there's a lot of industrial utility there.
Yeah, I think that's a really good point. That's where the strengths are, is in processes and optimization. And I personally think that like human intelligence and machine intelligence are fundamentally different. We're creating a world of collaboration where each individual person has, an area of expertise that they've got a synthesis of a certain body of information, but they don't have much expanse outside of that. And it's really hard to understand adjacent areas. And so the agents help us to better be informed of like different areas that are close to that niche, even much further out, generate better hypotheses. But there's always going to be a taste component, I think, of people, especially a new discovery like you were talking about, where it's like getting to a new novel concept. I think we're getting into a world where every individual scientist has like so much more leverage to explore and to like find new threads to pull on. And then the AI will help pull on that thread and unravel kind of the tapestry in a way. Like, I don't know if that's a great analogy, but.
Have you used any of the kind of AI lit search tools, whether it's, Edison or Cosmos or what do you think?
I think I think they're interesting. I think like Perplexity, I've used a decent amount, and we built some. And I think that what happens is they come to interesting ideas, they compete, and the agents are kind of like using this competitive process to compare ideas against each other. And in the end, it comes out a lot of times with interesting hypotheses, interesting concepts, but it's really hard to be able to like analyze all the exhaust that comes off of that. How do you know like that it's making the right logical conclusions? And so that's where I think the challenge comes. It's still a little bit hard to kind of fully trust the system that it's getting to the right conclusions.
And you can't just ensemble them, sort of basically have one AI fact check the other AI.
You can, and it does a pretty good job. And so I don't want to downplay. I think that like super valuable and exciting. I think just also fundamentally one of the challenges is that the literature is incredibly flawed. There's a lot of assumptions that are coming out, and so that's one of the reasons why we as a company focus a lot more on kind of methods, because they're pretty verifiable.
Interesting. Computer science doesn't have this problem because it's by definition verifiable. You just, run the code.
Yeah, exactly.
And the more biology can start to look like computer science, and that is replicatable, and the methods are fully described, and that like it compiles. Yeah, for lack of a better word, the happier we'll all be.
For sure. I want to be mindful of your time. This has been really
Thank
fun.
you.
Is there anything that we didn't talk about that you wanted to mention? Anything that you want to plug?
No. No, no, no. This has been a lot of fun.
Thank you. I really appreciate it. It's been a fun conversation. Well, I think it'll be really interesting to have this conversation and to further it in a year from now. Like, where's
Yeah.
the world going to go? There's so many interesting options. Let's see. I'm excited to see the future, man. Thanks so much for coming on the podcast. And, it's really, it was really fun to kind of shoot around some ideas with you. I think this is probably the most exploratory episode I've done in a little while.
Wide ranging, yes. So mile wide, inch deep, but
No, it's perfect. It's perfect. It's like this is exactly why it's like good to have different people come in with different areas of expertise, right? Because like we're all exploring this future together. We're trying to figure it out. And like, I don't know. I would say I know as much as many people, but like we have to like build this conversation, and we have to like
absolutely,
and we have to build it together.
No shame in confessing to ignorance in some part of the domain, because there's just so many of them.
Exactly. All right.
Yeah.
Thanks, Chris.
Great thing.
This is the Once a Scientist podcast. I'm Nick Edwards. We're back with new episodes, so keep an eye out and subscribe to the podcast if you haven't already.